All right, last time we were in the middle of discussing automata classifications and we got through one. I realized time was up and people were starting to enter the classroom, especially hearing that it's me, since I teach the next class that's in here as well. They're like, hey, I am ready for the next class. So that made me realize it's time for this class to be over. So we were talking about different automata classifications. The first one was a deterministic automaton. And that just says that for every state character pair that you're in, there is a deterministic transition to take. There's only one possible way to move forward. If I'm in state 3 and the next symbol that I'm reading is an A, there is a guaranteed single transition that we take from that state. And that will always be true for every state alphabet symbol pair. A non-deterministic automaton says that in some given configuration, and again, remember configuration is just that term for a state input pair, there could be multiple transitions defined or no transition defined, which means automatic failure. So it could be that there is a branch. You could go down this path, you could go down this path. And we'll talk about non-determinism in a bit, but basically, theoretically, we're going to be exploring them both in parallel. Because of this, it's difficult to think about this in terms of how a computer would treat it, because computers are all deterministic. But we can theoretically think, what about non-determinism? What if we could model non-determinism computationally? These are a couple other classifications. They aren't related to deterministic and non-deterministic, but in terms of the output of an automaton, it can either be an acceptor, which is going to say yes or no to a particular input. This is mostly what we're going to be doing in this class, is looking at acceptors. It'll ask the question, is this string in the language that this automata accepts? If yes, then we will output yes. If it's not in the language, we will reject that string. So an acceptor just answers yes or no. It's a binary output. On the other hand, a transducer can actually produce real output, an output string that's not just yes or no. So computers, in their base sense, are transducers. We can, with a programming language, write a program that produces actual output that's not just yes or no. But we will be considering a lot of yes, no, because that is what compilers do. Their job is to determine yes or no, is the program that you wrote syntactically legal in the programming language that the compiler recognizes. Where do we see these things? So where are everything we've talked about in the slide deck so far, formal languages, grammars, and automata, where are they used? What's the point of studying them? Any syntax diagram for a programming language, this is used at the theoretical or creation step. Or if you want to create a new compiler for an existing language, there's nothing that says that the existing compilers that are out there for those languages are the best or most efficient compiler for a particular use case for that language. So you could just design a new compiler, in which case you might want to utilize some syntax diagrams. When you do this, you'll be thinking about formal language and the grammar of the compiler and how you're going to translate the higher level language down into the lower level language. What is that process going to be like? How can you make that more efficient for the use case that you want to write this compiler for? So yeah, syntax diagrams, grammars, we'll see both of those in this class. Compilers as a whole, we'll study them in the broad and implement portions of a compiler. But with 10 weeks, there's not really enough time to implement an entire compiler unless I really hated you more than I do. It's also useful to just reason about the correctness of a program. If you can think about it theoretically, then maybe you can come up with a theoretical argument for why it's correct or not. Converting a language into another language. If you wanted to write some kind of, I don't know, C++ to Java converter, it's very similar to a compiler, because a compiler is just a language converter. It's just converting a higher level language into a lower level language, but there's no reason you couldn't convert a higher level language into another higher level language. Not particularly used as much, but you could do it. And I wanted to give you an example of a transducer, because all these others are mostly acceptors. I guess the converting of one language into another is more of a transducer, but binary adders as well could be considered to be automata. Anything that you could reduce down into the EE domain could do that. Any questions on some applications of this? I should really add one more humor bullet point, which is discover and be able to articulate why English is such a terrible language.
Finally have ammo against those English majors I know.
We've had ammo against them for a long time. We have job prospects. Since the era of Shakespeare, we've had a leg up on them. All right. Next big topic, we'll spend a little bit of time on this. Probably take all day today, a little bit of time next week. We're going to talk about our first automata type. And we will show a couple different versions of this, but this is really where the class is going to start becoming a little bit less of me talking at you and you working together to solve some puzzles, which is much more fun than listening to me talking. I probably should stop doing this and switch this, but I give the formal definition first, and then we're going to dive into an intuitive explanation of what this is. So don't be put off too much. Just like with what a grammar is, this is the definition of what a DFA is. So DFA stands for deterministic finite acceptor or automaton, either one of those I've heard the A used for, but it is a 5-tuple. Q, this first one, is a set of internal states. So think of these states as a graph. Graphs have vertices, edges connecting those vertices. So internal states are just the vertices of the graph that represents the DFA. Second, your sigma is the set of symbols in the alphabet. So what symbols could we be reading from the input? Then we have a transition function. Delta is just the cross product of the states and the symbols. This is just giving you every possible configuration of the DFA so that we say we have to have a transition defined when we're in a particular state and we see a particular symbol. So that's just the list of transitions of one state to another state when we see particular input symbols when we're in certain states. We then define a member of the set of states that is called the initial state. As I draw these initially, I'll start labeling them Q0, Q1, Q2, etc. You can use any naming scheme that makes sense to you. And sometimes I will label the states with something more intuitive than that, just to show what each state represents. Just like variables can have names that differentiate them from other variables, and that adds to your program's clarity. The names of your states in your DFA can also help understand what is the purpose of this state logically as you're trying to construct one to solve a particular language. And then a subset of those internal states called F that are final states. If we end reading the input and the state that we're in is one of these final states, then we will accept. If we end and we are not in one of these final states, then we will reject. So that differentiates the accepting states from the rejecting states, the accepting strings from the rejecting strings. You will always start in that initial state. Then the transition function defines exactly where you're going to go from there based on the input. And then once you're done parsing the input, the question is, which state are you in? Are you in a state that is in the set of final states? Or are you in a state that is in the set of non-final states? And that determines acceptance, rejection. So probably a slide now to talk about exactly what that is. So initially, we assume that the DFA is in that initial state, Q0, or whatever it is that you name it. The input mechanism, whatever is reading the input, is starting on the leftmost character, and it's going to start parsing from left to right. Remember that from yesterday, we cannot go back. So whenever we see a symbol, we have to make some associated transition in this automaton, and then we move on to the next symbol. And that says that in linear time, with one pass over each character, we can parse this and determine acceptance or rejection. For each transition, we're going to advance one position in the input string. We consume that input symbol because we can't go back to it. And we make one transition in DFA based on that transition function. So based on its configuration, which state we're in, which current symbol we're looking at, note that that doesn't depend at all on the past symbols. We don't need to store that information because it's irrelevant. It has a nice Markov property to it for those who have seen anything related to Markov. What matters is just the state that we're in, not the history of the states that we've visited. So an example would be the transition function when we are in state Q0 and we read an A, then we end up in Q1. So this defines an edge between Q0, a directed edge from Q0 to Q1 with edge label A, if we're thinking of drawing this out as a graph. In English, if the DFA is in state Q0, reads an A from the input, it transitions to state Q1. Looks like it has no juice. We're feeling orange today. I think there's juice in here. I tend to bleed these markers dry. So visualize them as transition graphs. I'll give you an example so that we can show you what that's like. So Q0 is the start state. You indicate this with an arrow. So some arrow that starts outside of the DFA and points into the starting state. That will visually tell you that that is where to begin. Input alphabet is going to be binary for the moment. And Q1 is going to be a final state. If the DFA finishes reading an input, is in a final state, we accept. If it's not in a final state, we reject. So here's an example. It's a directed graph. There's an arrow from nothing into some state that tells us that that is the initial state. If you use a consistent naming scheme like Q0, that can become implicit. But I will always expect that the starting state has an arrow just to remove any ambiguity from your drawing. So get used to doing that. I tend to forget it myself. It's hard to remember to do. It's the most useless part of this in terms of remembering to do it, because especially if you use this naming scheme, it should be implicit. But try to remember to include the arrow. From Q0, if we read a 0, we stay in Q0, so there can be self edges. If we read a 1, we transition from Q0 to Q1, which is a final state. From Q1, if we see a 0, we go back to Q0. Note how this is deterministic. For any state number pair, there is only one edge out of that state, and exactly one edge out of that state. There's no instance of a state where there is no defined transition on any binary digit. There are not multiple transitions defined out of a state for a given binary digit. So one question I might have for you is, what language does this DFA represent? It becomes a little bit more challenging. There's a simple answer that's wrong. This is a little bit hard to find and justify without some additional tools.
I mean, I'm just taking a guess, but is it like any string with a even number of ones in it,
If we just see 1,
or an odd number of ones, I should say?
what happens if we see 11101? It has 4 ones in it, which is even and ends in Q1. It's challenging. It's challenging without further notation to be able to figure out exactly what this is. It's not necessarily a language that is easy to describe verbally or in English. But we will find ways to describe in notation exactly what language any DFA represents, even if it's not something that is easy to describe. So I don't want us to necessarily go into that at the moment, but starting to think about and look at this diagram in terms of what does it accept is the kinds of questions that I will be asking you in a bit, with ones that are more readily apparent what they represent. questions on reading this, understanding what it does, acceptance versus rejection, tying everything I just talked about to a visual representation?
Well, I guess just one, I think it's already clear, but so if the circle has, if there's two circles, that's a final state.
Yes.
If there's just one, it's not. Okay.
Yeah, so yeah, the two circles here represent that the state is final, the single circle, I did not mention that, thank you, is a non-final state. So the empty string is not accepted because you start and you're done right away. Whereas if you're in a transition, which is a 1, now we accept. 1, 1, we end up in Q2, you know, that for any particular binary string, there is only one state that this can possibly end at, which either accepts or rejects. So it gives us a complete function for accepting and rejecting binary based on some language definition. So we could construct a machine like this to accept any language that this class of automata can represent. It turns out that there is a limit to this. We'll talk about that later. But this can represent a class of relatively simple languages, which end up being very useful in the construction of a compiler. We'll talk about that as well. Let's start with some just thinking about what a DFA can do. It accepts one and only one language. Why is that? Why is that intuitive? How do you see that or think about that? Yeah.
Because it's only programmed to read the inputs for that specific language. And you know what I mean? Because it's following the if else branches from each and every letter.
Right.
And that might be different depending on language.
Yeah, it's a complete function, basically. So for every string, we're either going to accept it or reject it. So there become natural rules associated with what does it accept, what does it reject, and that is a language. So there's a one-to-one mapping. It doesn't necessarily go in reverse. I'll actually ask that later, but the answer to that question is there can be multiple DFAs for the same language. They represent the same language, but given that you have a DFA, it represents only one language. Oh no, it's right there. Two different DFAs that accept the same language. The answer is yes. That said, is there a minimal DFA, a DFA that has the smallest number of states? Given this, if you were comparing two DFAs, how might you determine that one is better than another? Fewer vertices and edges. Usually a good thing to do. We'll actually talk about that and go into detail on the algorithm for reducing a DFA into its minimal state. But let's get you starting to think about this. So let's start with find a DFA that recognizes the set of strings on the input alphabet AB that start with the prefix AB. Once we see AB, we don't care what comes after it. Go ahead and give this a shot. Work with your neighbor, work in small groups, collaborate, and see if we can come up with a solution. I'll give you a few minutes.
Starting position. Let's see. And so we don't really care when you see whatever this happens because it could have B, 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 A, B, A, B, 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 and it's fine, right? Yeah. So if it's B, then it's obviously going to return back to the starting point.
Well, actually, I think because then we wouldn't want it to, if the B occurs first, we actually wouldn't want it to be able to progress even on the final states. So I think we actually need to have like a failure, basically like a failure
Bar state is what I.
bar.
It's a trap.
Oh, yeah, but then I think there's an issue. It's like just want to know that.
Oh, yeah. And then if this is an A, then it goes back to the failure state.
So yes. A, A, we're in
Yeah, you're right.
So
That's an interesting question on the failure.
yeah, it wasn't. Wasn't necessarily expecting this. I think it's right. So, oh, I think it's good. Yeah, yes. It seems easier to work from like the definition to the automaton than from the automaton to.
With the two examples that I've given you, I do not fault you for thinking that. That's probably true in general anyway, with how computer scientists think.
Yeah.
We like to go from a definition to an abstract solution, abstractly creating that solution. That's something that's been ground into you in past classes, something that's been trained. But
Right.
going the other way is not something that's been trained quite as much.
Right.
Look at a program, tell me what it does. That's not done quite as frequently as hit a problem, write a program that solves it.
Yeah. It's hard. Yeah, reading code is hard. You have to do that a lot of work.
Yes.
Skill.
We don't
Yeah.
do that enough, and I'm actually gonna be, I've built that into AI for Cyber as something that I think we really need to train people on to do better.
I think after we read like SDKs, libraries and stuff, it's like.
Yeah.
What do they do?
You think we have a solution?
Yes.
Anyone want some more time to continue working? All right, let's come up with a solution. So we know we need some kind of initial state Q0. Do we accept the empty string? Should this state be final? No. So that just tells you right away, a good first question you can ask yourself, does this language accept the empty string? If it does, Q0 needs to be final. There's no way to transition in a DFA without reading anything. So we have two possibilities of a symbol that we can read from Q0, A and B. One of those can be part of a solution, one of them cannot. If the string starts with a B, can we ever reach the prefix AB? No. So we're going to create what we call a trap state. And I like to draw those just kind of downwards, like you've fallen into a trap. So on a B, we're going to go to a state that we're going to call Q1, and any trap state has an edge from it to itself on every possible character. And you can concatenate those together just so you have fewer edges if you want. I can easily read what that is. On an A or a B, we stay in Q1. So as soon as we read this B, there is no way to get to an accepting state. No matter what we see from then on, we're just going to continue to cycle and loop from Q1 to Q1 to Q1 to Q1 to Q1, where we eventually run off the end of the input and reject because it's not a final state. Any Star Wars fans? On an Akbar state. On an A, on the other hand, we don't want to go to Q1 because that is the first part of the prefix. We cannot read multiple characters at the same time, so we need to define a second state, third state, I guess, Q2, that is the intermittent point between seeing this prefix. What happens if we see an A from Q2?
It's a trap.
There's no way to generate the prefix AB after having seen AA, so we're gonna take this down to our trap state. We do not need to define a second trap state for this because it is equivalent. Being here in Q1, it doesn't matter if you read B or if you read AA. Regardless, there's no way to get to a potential solution from there. So we don't care about the history of how we got to Q1. It's equivalent once we are there. We cannot accept. From Q2, if we see a B, then we go to an accepting state because we've seen the prefix AB. From there, we just need to loop to itself on anything, because once we've seen the prefix, it doesn't matter what follows it. we're already going to accept whatever comes after it, doesn't matter. So we are just going to loop from Q3 to Q3 on an A or a B. And this solves the problem. There are many other DFAs that also would have solved this problem. So if you didn't get exactly this, don't worry about it. As long as you believe you have a solution, or you can come check with me after class. Is this solution valid? Happy to take a look. Does this solution make sense? Do you see that this drawing solves, it's a state machine representation of this language? Any clarifications I can make? All right. Because this is a slide that gets uploaded, I felt like including a solution on the slide itself. So there's one of those as well. Let's try another one. DFA on binary, accepting everything except those containing the substring 001. Now, it doesn't have to be a prefix or a suffix. If at any point, anywhere in this binary number, you see 001, we reject. We hate it. If we don't see 001 by the time we reach the end, we accept. It didn't contain that evil substring. Little known fact, 001, best SQL hack ever. Not actually.
Easy way to start.
Yeah, that's the trap state.
Every other state is also acceptable. Oh, gosh.
We can have the start state here. Because it doesn't matter. And then if any time the other option is like, if this is a one, it's going to come back on itself.
And they all come back.
Yeah.
Yeah.
Yeah, because if it's a one, then. Or if it's a zero.
Come to here. Wait. Oh, no. I can't do that. These are all seven.
This has to be zero.
Oh, okay. Another pretty similar.
Yeah, so it is 1, 1, 0, 0, 0. If we have 0, 1, 0.
Yeah. 98% sure.
And also to accept the empty string because the empty string doesn't contain the substring.
Oh, yeah.
So we're fine on that edge case. Oh,
That was.
yeah.
Speak. Between code and. Zero.
No, but it goes back on itself. Because if we're repeating 0 multiple times after it's all done twice,
Oh, that's true.
then we're still going to be here.
So. Anything more than. Yeah, you're always in danger. So you reach to zero.
Yeah, because you can't do anything else other than keep pressing 0 as you fill.
Yeah. Yeah, not having zeros, you have. Then a one, it's bad. Yeah. Yeah. And might actually like take us. Shot one of these out. Would it work if we made B and C the same?
But then we have 0, 1 as an option. Because if we had A, we didn't have B, right? We'd have 0, 1.
You're right, yeah.
Anyone with a solution so far?
We're 98% sure. Got it.
How many states are in your solution?
4.
That is the minimal number of states.
Yes.
Just start over. I'm just gonna go from the edges of right there.
Well, partially. You can go wrong, but still have a prefix in it. Think about what happens if you have 0, 0, 0.
Yeah.
You've still seen the 2 zeros of 0, 0, 1.
You don't get a 1. Yeah, so you're such a pretty good odds. You ever see Interstellar?
That's the end.
Yeah, you know, it's we're just like they're smashing their heads together. It's like, what are you doing? We have a 50-50 chance. So one of us is gonna die. Those are the best odds of that.
How students feel in my classes. It may help you to design this without the Q0 terminology. I like to think of this in terms of the states being the portion of the substring that you have seen so far. Now just put in the connections. Given that you see the next digit being whatever it is, where do you go? And which of these states are final? We want to reject as soon as we see it, although we want to accept everything except those containing this. So we would want every other state to be final except for 0, 0, 1.
Thank you.
So it's easy to build the 0 when we see it. From here, we see another 0, we go here. We see a 1, we go here. The harder ones are the others. So from here, when we see a 1, what do? Move back to itself. We still haven't seen any portion of 0, 0, 1. From 0, what happens if we see a 1? Back to the initial state. So we haven't seen any chunk of 0, 0, 1. From 0, 0, what happens if we see a 1? We haven't seen any part of, so we see a 0 from here, what do we do? Back to itself, because yes, we've seen still the last 2 zeros of 0, 0, 0 are the first 2 digits of 0, 0, 1. From 0, 0, 1, what do? I guess we also didn't do a 1. We have a 0 and a 1, we have a 0 and a 1, we have a 0 and a 1. So all we have to do is define transitions out of 0, 0, 1. What do?
Back to itself.
Back to itself. It is the trap state, but it's the trap state at the end now. So I like to try to make this as logically intuitive as I can. And I pick my examples, try to introduce new kinds of logic. And one of these is that naming your states something other than Q0, Q1, Q2, even though that's what I will most frequently do in this class, can be a nice logical part of putting together a solution. So if you throw anything like this on a homework, I don't care what you name your states. Name them whatever helps you to solve the problem. The names of states don't matter. What matters is that you have a logical solution that is correct and complete.
Would you also be grading these on efficiency?
Only if the question asks for it. In general, I more so care that you have a solution than you have the best solution. Questions on this construction? why it works for accepting anything except 001. Strings with a substring 001, I should say. All right. As before, I have a solution to this on the slide, so that you can refer to them later and remember things without having to look at exactly this point.
Actually, I have a question.
Yeah,
I guess I don't really understand the idea of the trap state. If it is in the trap state, is it assumed that it is syntactically incorrect for that language?
it means that, yeah, we found somewhere in this string, we found that substring. So in order to be in this state, we had to go at some point and see a 0, 0, 1, or a 0, 0, 0, 0, 0, 1 at some point where that substring existed. So given this construct, if we start with any binary string here, we will end in one of these three accepting states if it does not contain the substring 001 somewhere in it. But if it does contain the substring 001, we will end in this state and reject. So now we have a classifier basically for all strings that do or don't contain that particular substring. So this becomes a solution to that problem, which is quite cool. Great question. Other questions? All right, let's talk about, before we dive into another example, let's talk about the class of languages that this actually solves, or it can represent. So no matter what you create, any finite automaton, like a DFA, we've seen that it accepts some language. You can now think in the broad. Given the rules of a DFA, imagine the set of all languages that such a construction could represent. So we will define the term of a family of languages, those that are related by some efficiency metric or complexity metric. Is it limited? Is there a language out there that a DFA cannot recognize, no matter how complicated the construct? Yeah?
Like concatenate with its reverse. If you require memory to solve it.
Yep, yeah, that's exactly right. So DFAs don't store memory. There's no history. So as soon as you need some kind of history to be able to answer that query or to be able to represent that language, then a DFA cannot represent it. The simplest example, well, that is a great example, is a string followed by the reverse of that string. We need to know when the string ends and the reverse begins. That could be anywhere in the string.
And it's also impossible to have every single DFA branch for that because you can't account for.
Right.
Yeah.
The DFA has to have a finite number of states. And there's no bound on the length of this string. So if you had a DFA with 1 million states, you could handle up to 500,000 characters and then 500,000 characters in reverse. But as soon as I give you 1,000,002 character palindrome, suddenly it won't work anymore. So you could add more states to the DFA, but eventually you have to be done and say, this is the solution, in which case I just give you a string that's bigger than that. So we will define any language that a DFA can accept as being under the set of languages that we will call regular languages. Anyone used regular expressions in text? Same thing. Whatever you can write a regular expression for, a DFA can represent. Same class of languages.
Okay, can't regex take an infinite number of inputs with answers.
It can take a repeated number, can say 0 or more, but then it has to have structure to that.
Right.
But so can this. If we have a self edge, we can say 0 or more by, yeah, going back to itself. But as soon as we need to represent any combination of it, then we need those branches, which becomes intractable. Great point, though. So a question I might have for you mathematically, how can we prove that a language is regular? Solution to this is way simpler than I make it sound.
That way you can use a DFA.
Draw a DFA for it, yeah. A mathematical proof that a language is regular is if you construct a DFA for it. Done. Really easy question to answer. So draw a DFA for it. We will also go over a couple other ways to prove that a language is regular with a couple of other classes of ideas. But because this is how we're going to be proving that a language is regular, it's worth actually getting practice in constructing them. So if I were to ask you a question like, prove this language is regular, you just draw a DFA for it. So let's get a little bit more practice, making it a little bit more complicated at a time. So example problem number 3. Show that the language A followed by the string W followed by A, such that W can be anything in the star closure of AB. Recall the star closure is 0 or more instances of anything from that set is regular. So this is really just saying strings that start and end with an A.
But there needs to be a minimum of 2 A's, correct?
Yeah,
Okay.
have to start and end with an A, but there have to be a minimum of 2 A's, yeah. So A doesn't work. So it's not quite a perfect translation.
Well, this doesn't have to be an A because it's also an empty string. It's just a start point.
Oh,
Theoretically.
yeah,
And
we haven't seen.
yeah, we haven't seen it yet. You can just add it.
Start. Okay, but we have first day.
So the ones that let's combine, so it's A, it's B, it's gonna put into drop state.
Failure. Match up with E or emotion. A. Get a B, take us to the middle stage.
Maybe let's think about this for a second. So if it's an A, right? We can go back over here as well, because technically that would be to meet the requirements, right? Because AA is legal, AAA is legal, AAA is legal. So if we have a repeating A over here, we're also fine. So A going back to itself. Okay.
But we can't end with a B.
No, if we end with a B, we can go back over to here because we still start with an A, we just don't end with it. So this is just A something. This is A something A.
Oh, yeah, I think
So
it's
I
just
don't think you need
don't
to
need
say. Yeah. At least I don't think so right now. So
Oh.
the only thing that we're missing here is we need the reference of where B goes. But if you have B, then when you have A, then something, you're still missing B, I think. So B can reference itself.
just comes to itself. I think, yeah, I don't know.
I think.
I think that would.
Those of you who have a solution, how many states are in your solution?
We're double checking it.
Or is the minimum answer again?
That works, right? Yes, once we got our first day, it's almost impossible to fail unless you meant the B.
Yep.
So it's
You just try to leave, yeah.
getting a B, it's just incomplete. But you can't get trapped, as long as you get A.
Yeah.
So that way. Is it?
You just need an A to end it. So it just depends on your.
Yeah, so then you. A, and then that's right. Start with B, start with start. Well, yeah, it's just not. String. Yeah. It's. Yes. Yeah. So we get this. Awesome.
Start with the easy one. How do we construct the rest of this from here? We see a B at the beginning, we know it doesn't start with an A, there's no way it could possibly be in this language. So there's a trap state for it, if it starts with a B. However, if it starts with an A, now it's interesting to us. What do we want to do from Q2?
I made a state, it's like dedicated to processing. So I went on a B, you go to a new state, that loops back on itself on a B.
Okay. So make a new state. Q3. That loops back on itself on a B. Did we do that in Q2? I do think we need this new state. But this is gonna be our accepting state. Once we see, we're gonna assume this is the first A, and this transition will be a last A. Potential. So we would want to loop here on a B. But is it complete? I mean, we need something in Q3, but what finishes this off?
Don't you need Q3 as final, but if you see a B, you go back.
Yeah, we see a B from here, it was not the ending A. What happens from Q3 on an A?
Go back on.
It's back on itself. So one of these will be the last A. But if we see AA at the end, we want to be able to do that. Is there any way to get to Q3 without seeing two A's, the first one and the last one? No, so this does not just accept A. So I buy this, I think this is correct. But the common mistakes that I would see here would be accepting a single A. Somehow being able to end in Q2 on an accepting state or on an accepting string. But take a second and convince yourself that there is no counterexample, no string that's not in this language that ends up in Q3. There's no string that is in this language that does not end up in Q3. Any thoughts on that? Does it make sense? Does it seem like a complete correct solution? All right. We're out of time somehow. Time flies when you teach the content way faster than it does when you're in a seat listening to a lecture. So I do have one more example problem for us to start off Monday's class. My goal is to get up the first assignment. I don't think I can reasonably make it due on Wednesday. So I will probably make it due a week from Wednesday just to make sure that you have enough time. But do note that I might try to assign the second assignment while this one is still up, making it due the following Wednesday. But I might want to at least get you the content so that you can get started on it sooner than that. So my recommendation for this class is get started on homeworks early. I know that the TA posted in Discord a little hint of, it took me about 45 minutes on average to solve a particular problem. And of course, I assign 10 or 12 of them over the course of a week. So it's going to be a lot of work to make sure that your answers are complete and correct. And it will get more and more complicated throughout the quarter. Start that process early and you will run into fewer issues, especially on those last couple days where my poor TA and I are swamped in office hours and it's harder to get your questions answered in a reasonable period of time. I try to parallelize to the extent that I can and have 6 people in my office if you all have similar questions or can learn from each other. So you're not just waiting for your individual turn and wasting a bunch of your time. That said, if there's the entire class there at once, you don't necessarily all fit in my office. If you all have slightly different questions, it can take longer than the amount of time that either of us have if all of you wait for those questions to happen the day something is due. So whatever extent possible, start early, get stuck early, come to me for help. I would love to talk you through some of this, come up with some alternate questions and walk you through how to solve problems like this. So get stuck early, come see me. I love talking about this stuff. Is there a question?
Do you do like all reviews after their trip?
I do.
Like, do we go really something like? I think that-
That would be amazing if we had the full time. I usually end up going over it if you have questions about it in office hours. Just because there's too much actual class content. But it'll take the whole 10 weeks to cover all of that. But yeah, I'd be happy to go over any problem from the homework in my office. Awesome. Have a great weekend. I'll see you on Monday.
This was,